I'm paying a lot more attention to how we can use some of these ideas in our teaching. And the whole story started in 2019 when I came across this really excellent book by Ording called 99 Variations of a Proof. Has anyone seen it? Yeah, one or two people. I don't know whether it's going to remain on my best 10 maths books list ever. It might just a case that the right book came along at the right time. What he does is he proves a particular theorem in 99 different ways and uses that as a discussion of style. And I really enjoyed reading this book. It really made me think about proof and about mathematics in a new way. And the theorem that he proves is this. X cubed minus 6x squared plus 11x minus 6 is equal to 2x minus 2. So he's got a cubic curve and it intersects with a straight line. And if the cubic curve intersects with a straight line, then we have two roots. So one of them must be a repeated root. Well, yes, it's a theorem at a very technical level, right? You can describe it as a theorem. That's absolutely fair enough from a pure mathematical sense. It's not what I would put as a theorem in a proofs and problem solving course maybe. But there it is, and I really enjoyed the book. And some of his proofs are just flat out outlandish. I mean, getting to 99 proofs is a tall order, so some of them really are just completely bizarre. Here's one of his proofs by picture. So he starts, you don't expect to read this, but he starts out with x cubed. Here's the slab x that he takes away, then he adds in another x, and then he takes away another x. Squared and so on, right? And eventually gets down to the cuboid, which must be x minus 1, x minus 1, x minus 4, so he solved the problem, that kind of thing. But there are some even more outlandish proofs in this book, and I really enjoyed it, so I commend it. And then December 2020 was not a happy time. End of semester one was exhausting, and then the second lockdown came along, and so instead of a week at Christmas with family, I had a week at home on my own. And sunrise in Edinburgh around the 21st of December is approximately 10 to 9 in the morning, and sunset is 3:15. So at best we have 6.5 hours of the sun above the horizon. So there's a lot of time to sit and think. And I was separated from my books, which were now in my office. And so I just decided to do something entirely self-indulgent and write my own collection of proofs, right? That was, just sit down and write as many proofs as I can of my own theorem, because I just enjoyed this book so much. And I chose the sum of the first n odd numbers starting from 1 is n squared. I hope is familiar to many of you. It's a very famous theorem. I knew that there was a famous proof by picture, which is nearly 2,000 years old. So there was a really good picture proof. My PhD student is looking at how to assess proofs online. Igor mentioned my interest in online assessment, so how can we assess proofs online? And specifically, she chose proof by induction as a vehicle to run some studies. So she and I looked at how proof by induction is taught, the history of proof by induction, the kinds of things we use proof by induction to prove, and so on. And as part of that work, it is claimed that the first modern proof by induction was written by De Morgan in this book in 1836, and that's the theorem he chooses to use, right? So there was this kind of historical link there, and I just knew that there were a whole bunch of other proofs. So I sat down and proved it as many ways as I could, and then I looked on the internet a bit, and then I carried on collecting these proofs. And about that time, I was sent a preprint of this really excellent paper. And mathematics assessment of the explanatory value of proof. And what this does is it used comparative judgment to investigate mathematicians' notions of explanatoriness. And in common with many of the best papers, it irritated me, and it irritated me so much that it actually took some action, and I did some things as a result of that. Now, they did a comparative judgment experiment, and they validated comparative judgment methodology, but they only investigated one scale. So what they did is they asked mathematicians, in each paired comparison, we want you to think about which argument best explains why the proposition holds. Okay, so this is best explains. And they used the theorem from Ording's book, which, is not, it's all right as it goes. They did use sensible proofs from Ording, so I'm not going to, they didn't use any of the really crazy outlandish ones. They did use that picture proof. Right, so anyway, that was the starting point for the research that I'm going to report, is that we had this very interesting paper. But I was interested in investigating rigour and insight. Okay, so investigating understanding is one thing, but what about mathematical rigour? Do we all agree on what is and isn't a rigorous proof? That seemed to me to be that's where I would start. So I thought, well, I'll do that. And also, I wanted a real theorem, and I wanted real proofs that might occur in the wild, right? I mean, I put that in quotes because it's my view. So, and I had those to hand. You know how some things just come together in a happy way. So I thought we'll just do that. And I've never used comparative judgment. I know Ian Jones at the previous seminar spoke about comparative judgment, and I will explain what that is in a moment when I talk about the methodology. But it's I'd never used comparative judgment myself, and Ian Jones had just released a module that allowed me to do that. It was all set up in my institution, so all the methodology was there. I just never used it. So it was a good opportunity for me to try a new research methodology. So with George Kinnear, my colleague in Edinburgh, we did a comparative judgment experiment, and we investigated undergraduate students' conceptions of rigour and insight. So we had two groups. And what we did is we conducted some comparative judgment experiments, and we predicted, and our experiment found, that rigour is reliable. Okay? Right? It's a reliable scale. So I think on the basis of the evidence that I'm going to present, I think it is meaningful to say this proof has rigour. So whether that is an absolute property of a particular proof, or whether that's a social construct, doesn't make much difference because everyone agrees, basically, to a reliable extent. So we may have a philosophical discussion about where rigour arises. Is it a nature of the argument itself, or is it something we just all agree on? But nevertheless, it's reliable. And we also predicted that insight would similarly be reliable. There would be proofs that people found gave them insight or were insightful. But interestingly, that's not what we found. So we didn't find a reliable scale. So that what we mean by that is that we don't think people agree what that means. That was actually a big surprise. And we'll talk about that a bit. So comparative judgment. Basically, it's a very simple methodology. Judges are presented with two things, and you're asked to choose one of them. Okay? So you have to decide which is better. And you will be given some judging criteria. So for example, you will just be asked which is more rigorous. That's all you do. Okay? So you get repeated pairs of items. It gets fed into a model. You must make a decision. Okay? So you can't say I don't know or I'm not sure. You have to make a decision. That's an important part of the model. And then the pairwise judgments are all put into a statistical model, and you get a z-score which ranks the proofs according to the scale, right? And you get error bars and a reliability of the scale and a whole load of other things out of the statistical model, which I'll explain in due course. And this is being used in research and in teaching. It's becoming much more mainstream. It goes back to Thurston in the 1930s. I'm sure Ian would have mentioned that in his seminar. The internet allows you to do this, the orchestration of randomly pairing things, recording the judgments and then feeding that to a statistical model would have just been hideous 20 years ago, right? But now it's just, we're able to do that and we've got the tools. So it's becoming much more useful, and it's useful for situations which are not objective, where there is a qualitative judgment. You know, which photograph is better? That kind of situation. It's much more useful for that. So, you know, if we want to find out whether people agree on rigour, this is, I think, a reasonable methodology, and the previous paper established methodologically that this was a reasonable thing to do. So that's one of the major contributions of the previous paper that I've referred to. And why is this helpful? Well, it's much easier to discuss comparisons than absolutes, right? If you've got 2 cups of coffee, almost all of us will almost always reliably be able to choose the hottest cup of coffee. But it is very difficult to say what is the temperature of the coffee, right? So, and human perception is based on differences. That looks black, right? Does that look black to everybody? Yeah, but it's not, is it? If we turn the projector off, it's a white board. It only looks black because it's next to something that's brighter. So, you know, perception, the psychology, the low-level physiological mechanisms in perception are largely based on comparisons, not absolutes. So it's based on those kinds of things. And also then we can then discuss meaningful, we've got some actual data, we've got some objective quantitative data, we can then discuss why that might occur, and it's not just, well, I like that proof more, there is some real hard data that we can then use to make meaningful discussions of the differences and why they might occur. Rigour, I think, was uncontroversial. I don't know that anyone had established whether people reliably, whether rigour is reliable or not. I mean, it's a kind of urban myth in mathematics that we all know what rigour is when we see it, but I haven't seen any evidence that we do actually know it when we see it, right? I mean, there's a lot of educational research, basic questions that we still could pursue profitably. But insight, we're widely talked about in education, teaching for insight. We want to understand the proof, not just be told it exists. What the proof should do for the student is provide insight into why the theorem is true. Lots of statements like this throughout the education literature. I am sure I have written some on occasion. Okay, so Freudenthal, one of the most famous maths educators, how to keep open, his fourth problem, how to keep open the sources of insight. So do we know what those sources of insight are? How would we recognize them, right? I mean, that's the kind of basic question we wanted to answer. So that's why I chose insight. So what is insight? Well, insight is a change in understanding. Now that could be an aha moment, that could be an immediate, that's why it is, or it could be a more complicated, longer term, gradual change in understanding. But insight is a change in understanding. Okay, so that makes sense as to where I've come from and what I'm going to do and the theorem. So by this stage, I've got about 20 proofs. I'm now up to about 30. I think some of my colleagues are very glad I'm halfway around the world and they're not going to get plagued with yet another one as I show up. But we selected some, and these are the ones that we selected for the purposes of this study. Okay, so the sum of the first n odd integer starting from 1 is n squared. Okay, so here's the first proof, right? 1 is 1 squared, 1 plus 3, first two odd numbers is 4, that's 2 squared. 1 plus 3 plus 5 is 9. Okay, 3 squared, 16, 25, 36. It clearly holds. Okay, that's the first proof. We're done. Okay, now some of you may be thinking, Chris, that's not a proof. Okay, right? Some of you might be thinking that. Well, it will be no surprise when we look at the quantitative evidence from the participants in the experiment that everyone agrees that this lacks rigour. Right? Okay, so that's not going to be controversial or a surprise, but that's why it's here. Okay? Yeah, so that's the first proof. Here is the second proof. Yep, that's it, proof by picture. So if you look in the bottom corner, you've got 1, that's a square. The next one is you've added the 3, it's a square. Okay? So we add the next odd number 5, we add the x number 7. We keep adding odd numbers and we're just going to get a square. Right? This is a very famous proof by picture, goes back nearly 2,000 years. How many people have seen this before? Okay, yeah, so lots of people have seen it. It's a cultural artifact in our discipline. It's very famous. For one of my colleagues at least, this is his favourite proof ever. To him, this is what the theorem means. Come back to all that kind of stuff later on in the discussion. But some of you, certainly if there are students here, might have been told we shouldn't use proof by picture, right? It's not a proof. So we'll look at where that comes on the rigour scale with some interest. That's why we put this one in. And we'll think about where that comes on the insight scale, right? Does that make sense? So again, that was there for a reason. Nelson's lovely book, Proofs Without Words, this is where I got this one from. So it's clear here where the odd numbers come in. We've got 1, 3, 5, 7, and then you end up with n squared. You've got 4 copies of the odd numbers, and you end up. I'm not going to go through these in detail because I haven't got time, but if you're interested in these proofs later, you can have the proofs. It's an arithmetic progression, right? So it's first plus last over 2 times by the number of terms. This is from Euler's Elements of Algebra. It's in lots of other books. That's how he proves it. There's nothing more to it than that, right? Reversed lists. How many people have seen this kind of argument? Yes, right. So you write the thing you want to add on the line, you reverse it and write it in the reverse order, and then you notice the columns all total. Right, so we've got the first column is totals to 2n, we've got 2n here, we've got 2n here. So all the columns are the same, and we've got 2 loads of the, right, so. Telescoping, You can see, I mean, there are quite a decent variety of proofs of this theorem, right? I mean, so telescoping, you notice somehow that the odd numbers are the difference of adjacent squares. So k squared, k minus 1 squared. And then if we're adding up the odd numbers, we must be adding up the adjacent squares. And then when we write this out, the 1 squared here cancels with a minus 1 squared here. And the 2 squared here cancels with a minus 2 squared here. And everything cancels except the first and last. And we get with n squared minus 0 squared. So, okay, backwards reasoning. So the fundamental theorem of finite differences states that Sn is the formula for the sum of the series if and only if an plus 1 is this formula. So this is the difference, Sn plus 1 minus Sn, and S1 is A1, right? That's the fundamental theorem of finite differences. And then we apply it. So we consider Sn is n squared, and then we do our difference of adjacent squares and so on, right? Now, I do want to make a couple of comments about the fundamental theorem of finite differences, because it's an if and only if proof. So if you want to sum any series and establish the correctness of a formula for any series, this is the only proof that's always going to work for you, okay? Because it's the only one that's an if and only if. It also requires a formula for the answer in advance. The arithmetic progression, the n squared, drops out as the answer to what is the sum of this series. Whereas with this proof, you need to know the formula for the sum in advance, don't you? So when we were setting up this experiment, we were interested in not only things like, are picture proofs more rigorous than non-picture proofs, but other characteristics of proofs. So do proofs that give you the answer score differently than proofs where you have to know the answer in advance? Yeah? So we called those problem-solving proofs. Proofs where you get the answer are ones that solve the problem. I'm not sure that's the best phrase to describe those kinds of proofs, but I don't think we have an agreed vocabulary for talking about different kinds of proofs in those ways, right? So we were certainly looking at different kinds of proofs like that. You need some induction to prove the fundamental theorem of finite differences. So there's a hidden induction in the background here, although you're not doing induction, you're just applying the result. And actually, this is, for those people who are not familiar with this, and I wouldn't be surprised that you're not familiar with this, this is actually just the discrete counterpart of the fundamental theorem of calculus. So if delta is the first forward difference operator, Sn is Sn plus 1 minus Sn, then the sequence is the sum of the differences. Just as with calculus, the function is the integral of the derivative. Now, the an is S1 is exactly the same as having an anchor point, which is your constant of integration. Right? So it is the same, it's just a discrete version. And this is just forgotten knowledge, really. It's not taught, I don't know it's in any, there's a whole beautiful world of parallels between the discrete and the continuous that we don't teach systematically. But there it is, so we stuck that in as one of our proofs. Okay, rearranging. Yeah, we've got standard results like 1 plus 2 plus 3 is n plus 1 over 2. We all know that one. And 1 plus 1 plus 1 is n. Okay. So you can use those standard results and you can take your 2k minus 1, that's 2 lots of the sum to k, take away 1 lot of 1 plus 1 plus 1, and then you just plug it all in and you get n squared. Has anyone seen this kind of argument? Yeah, right. The other rearranging ones, there's no end of the rearranging ones, folks. I like this one. To add all the odd numbers up, you add all the numbers up and take away the even numbers, and the even numbers are twice all the numbers up to n, aren't they? Agreed? So you can just use this same formula once, 1 up to 2n, and then you take away the sum up to n, and then when you do all that algebra, it drops out at the bottom. Okay, we'll come back to that one. Proof by induction. Let P of n be the statement, blah, 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 blah. Okay. It will be no surprise if this is considered rigorous, will it? Really? Yeah. Okay. Proof by contradiction, just because we can. Right. And by this stage, because I am now getting into some of the sillier proofs, I do have some really crazy proofs now. We included this one in the study. We know it's got to grow like a quadratic because you can bound it by n times the biggest one. So we're just going to assume it is a quadratic and then set up a linear system and invert the matrix and we're done, right? All right, so now, you see, this is where sometimes a silly proof helps illustrate a new area of maths. I have a gap in my collection for complex analysis. So if anyone could come up with a contour integral, I would be really happy, but I'm not a strong complex analyst, so there's an opportunity there. If you don't believe in quadratics, you can just do an infinite series. Again, this isn't a very fashionable technique, but all the 19th century books had lots of undetermined coefficients. So you can do it that way. Those are the proofs we included, right? A whole range of proofs. Some of them very reasonable. These last two, not so reasonable, perhaps. And then just for completeness, and later on in the study, we did add two more proofs. I'm going to report 3 experiments. And in the later 2 experiments, we included a detuned proof by induction. So the first proof by induction was very much let P of n be the statement, da-da-da-da-da, da-da-da-da-da, right? I teach induction in the proofs and problem solving class. It's a template. My first year students must use the template, right? Okay? So that's what I tell them. Except no professional would do that. I expect a professional would do something like this. Okay? Consider this conjecture. 1 is 1 squared, and then it follows by induction. So this was a deliberately and consciously detuned induction. And similarly, this was a proof by picture where we added some words to it to try and make more sense of it. So we wanted to see if we could manipulate the proofs in predictable ways and get predictable results in our later experiments, right? So that's why we did that. So that makes sense as what we're doing. Okay. So how do we set up the experiment? Students were randomly assigned to 2 groups. One was the rigour group and one was the insight group. And we wanted to know, do students see rigour and insight differently, and what features of proofs might score high and low on each scale? That's the basic quantitative experiment. So we set the experiment up online. It's in Moodle, so that was easy. We recruited year 3 undergraduates on a maths degree. We prompted them to bring the judging criteria to mind, and then they had to perform the comparative judgment experiment. So the judging prompt was, they would log on, we didn't know which group they would be in, so they would see, please explain briefly in a few sentences how you would decide if a proof is rigorous. And they would type, a proof is rigorous if blah, 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 blah. And then the second group, if you were in the different group, you would get the prompt, please explain in a few sentences how you would decide if a proof gives you insight. Okay? So the idea of this prompt before the real experiment was just hopefully to ask the participants to bring to mind the criteria they're going to use in the comparative judgment experiment. Okay, that's the idea of this prompt. So once they've done that, they then did the comparative judgment experiment, and they would get randomly assigned 2 of these proofs, and they would just have to say, in each case, select the proof which is more rigorous, or select the proof which gives more insight. So they then read the proofs, they choose left or right, and then they get another pair. And we asked them to do between 5 and 20 judgments each, right? So that was, we didn't want people spending all day on it, and we only included judges who took it seriously enough to at least do a few, right? So, and we excluded some judges who took almost no time. If they just went left, 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 right. So we threw away the very quick judges with criteria. Anyway, here are the results. So this is experiment 1. Let me explain these results just so that we know what we're looking at. On the left here we have the output from the model for the rigour group. And these thetas are the output from the Bradley-Terry model, so it's a z-score. And each proof has been assigned an estimate of its parameter in this model, and the model gives you an error bar, right? So we can see that proof 10, that's proof by induction, no surprise there. Everybody thinks that is the most, basically, everybody thinks that's the most rigorous proof. And, you can imagine I was at least slightly pleased that number 1, the experimental evidence, the students agree that is the least rigorous proof. Okay? Fair enough. Right? And then all the other proofs are somewhere in the middle. And there's some separation, but the error bars overlap often, right? So that's what error bars do. And here is the insight scale. I'm not going to go too deeply into examining where every proof is on this scale because I've got 2 further experiments, but we will look on the right with the correlations. Now, it doesn't make any sense here to compare the theta from rigour with the theta from insight, right? They're not directly comparison. It's like height and weight. Okay, so they're different things. They're different scores. But we can look for correlations. And what really surprised us was the extent to which these two scales are correlated. Apart from the picture number 2, which is the very famous old picture with the L-shaped, right? And the two of the later proofs, so that is contradiction and undetermined coefficients, which were always slightly outliers anyway, right? I mean, I never really put those in as serious ways of proving this theorem. Apart from those 3 proofs, it's an amazingly strong correlation. Even with those proofs, it's frighteningly strong, right? So, and this was completely unexpected. I don't think for this group of students that there's a difference between rigour and insight for them. Okay. That was our conclusion. And when we looked into it a bit more carefully, and we looked at the judging prompts, what does it mean for a proof to give you insight, we got things like this. A proof would give me insight if it's clear and concise, all the terms in the process should be well defined, each step should be shown with no gaps in the proof. That's from the insight group. And if, we haven't done a thorough and rigorous qualitative analysis of all the comments from the insight group, but they're basically indistinguishable from the rigour group. So we concluded that our undergraduates don't really understand what we meant. So there's 2 possibilities. Either it really doesn't exist, there is no difference between rigour and insight, right? That's one possibility. Or the second possibility is that we just didn't do the experiment very well and they didn't understand what we meant. Does that make sense? So we did a second experiment to try and figure this out. So in experiment 2, we tried to replicate the rigour result. We tried to adapt the judging instructions to really communicate what we meant by insight a bit better. We also introduced some new groups, and we tried to find things that were least associated with either rigour or insight to establish that people can judge these on a different scale. We didn't really care what that scale was, we just want to know that they're not choosing some random best, which is the best proof, right? So we looked for a test of divergent validity. And then also, because we'd done the experiment once, this is when we added in those 2 new proofs just to see if we could manipulate proofs in predictable ways, right? So this time we did it with year 1 students because we'd already used the year 3 students, okay? So, right, we could replicate this again with slightly, I will, you're going to laugh because we did it with expert research mathematicians as well, so I'm going to report that as the 3rd experiment, so before we laugh at the first years. Okay, so in this experiment we had 5 groups. We had the rigour group. We changed insight into why the theorem is true, to try and strengthen what we meant by insight, right? Which proof is simple? Now, from previous work that Matthew Engels has done, simplicity was the least likely to be associated with either rigour or insight, right? So we chose simplicity, which is the simplest proof, to try and make sure that this was not just some random best. Again, to strengthen this idea of insight, we had an understanding. We had an understanding problem, right? And then last, we had which is going to get the highest marks. Okay, right? Okay. So we now have 5 groups. And then, so same process, bring to mind by asking you, what does it mean for a proof to be worth high marks in an assessment, right? You have to write that out. And then we do the comparative judgment experiment. So on the top of the screen it says, which proof would get the most marks in an assessment, and you just choose left and right. And actually, for some things, comparative judgment is now being trialled for assessment. So this is not such a fanciful way of assessing students. Okay. So these are the data that we got from the model before I show you the scales. The first column is the number of judges in each group, and the second column is the number of judgments that were made in that group. So there were 636 pairwise comparisons on the basis of rigour. I don't know why the randomization only assigned 25 people to the insight group. It's deeply frustrating because that's the group where we really needed the most participants. But that is the nature of the world, isn't it? There are words for things like that when they happen. Okay. SSR is the scale separation reliability. That is a reliability that you get from the model. Informally, and I'm sure I will get shot down for this, but think of it like a correlation coefficient. It's some measure of general goodness from all of this, right? So 0.7 is, or above is generally accepted to be quite good. So all of our scale separation reliabilities, even the insight group, meet that threshold. 0.94 is just exceptionally good, right? Split halves, what you do is you randomly split the group up in half, you measure you run the model on each half, and then you look for the correlation between the two models, right? And you keep doing that, and you get this extra score. So what's interesting for the insight group is that collapses when we go and do the split halves, which is why it's so disappointing we didn't have 40 judges in that group. Okay. Anyway, there we are. But we've got 0.7. If we hadn't done the split halves, which not everyone does, we would have looked like we're okay. But that's the way it is. But it's not about the number of judges, actually, because if you look at marks works really well. We don't need that many judges. When you've got a reliable scale, when the reliable scale actually exists, we have more than enough judges and judgments to establish the scale. So this really is evidence that people don't understand insight, or that there's something strange going on here. Yeah? So I think we don't have a reliable scale for insight. I don't think it's just a matter of going and getting more data. Okay, that's what I want to say. Okay, so here's the data. I have coloured these. Apologies if you're at the back. So let's do the easy things. Proof 10 is proof by induction, right? Everyone thinks that's the way most rigorous, that it would get the most marks, right? Interestingly, people report that gives them insight, and they report that gives them understanding. Okay? But it's not the simplest proof. The simplest proof is the L-shaped picture proof. So our participants are not just choosing some random best. This test has worked. Okay? So they are actually looking at the scale and trying to use the scale that they were given. Experimental evidence, again, was the least rigorous, and what's interesting, there's some discussion about marks here. Proofs by picture would get less marks than experimental evidence, according to our students, right? Even though proof by picture was the simplest. So kind of interesting differences when you start examining these scales in detail. Proof by picture to the students is not the least rigorous, not on its own. Some of the proof by undetermined coefficients was less rigorous than the picture, interestingly. There's a lot of overlap in the middle, so these are similarly rigorous, and there's a lot of uncertainty on the insight and so on, right? But there are differences in these proofs.
Sorry, quick question. Can you repeat or clarify the difference between insight and understanding? Those sound pretty similar.
That's why we put them in, right? Because in the previous groups, we don't think students understood what we meant by insight. So we had another group where we just said understanding, because that's what we had in mind. I think of insight as a change in understanding, right? Like an aha moment.
Either way, they're supposed to be about understanding why,
yes,
not about being convinced.
So that's why we changed the prompt to understanding why,
okay,
from insight into why the theorem is true. In the first experiment, we just said which gives you insight. So we tried to strengthen the insight prompt, and we introduced a completely separate group, which is really about understanding. Okay? And understanding why the theorem is true. Yeah, thank you. So that's exactly why we did this second experiment, so that we have all these these different groups. Right. So this data is quite complicated, and one thing that was interesting is we had lots of ideas about different kinds of proofs. So, are picture proofs more or less rigorous? What about certain kinds of proofs? And we couldn't see any real patterns here. Actually, that was a surprise. In terms of correlations, these scales are, again, highly correlated. So we did an exploratory factor analysis on the scales, and we found that simple had done its job. It did not correlate with marks, right? So they are independently doing it. But what we did find, these are the correlation coefficients, what we did find was that there are two factors that amount for 87% of the variation. That's pretty good. One of the factors is associated with rigour and marks, and one factor is associated with simplicity and understanding, and the insight just loads equally onto both. I don't think people understood what we meant by insight. Okay. So that's a pretty nice result, I think. Rigorous proofs get the marks, simple proofs help you understand the material. Right? There are correlations between those. I don't mean any causation there, right? Okay. So rigour and insight were still highly correlated in this experiment, and in spite of all our efforts to strengthen that prompt. So I don't think they can really be distinguished in the way that in the way that when you read some of the maths education literature, they really talk about these as easily identifiable separate things. I honestly thought these would be first order things that we would just see immediately. Some proofs would be strong on insight, some proofs would be strong on rigour, and we would just see that. We didn't get that. So there is a lesson here about care in use of language and care in defining what we mean, right? Not just talking about things as if we all understand and agree what they are. So yes, genuine independent judgments are being made, and lots can be said about the individual proofs. But I'm not going to do that. Let's go on to the research mathematicians. So this is self-reported colleagues. We emailed around UK maths departments. Are you a researcher, a PhD student, or somebody else? Do exactly the same thing again. I'm only reporting the researchers. Sorry, postgrads, you're somewhere between the undergraduates and the researchers on all of this, so I'm not going to report that. Colleagues think that experimental evidence is not rigorous and that induction is rigorous. They think experimental evidence will not get high marks and induction will get high marks. Interestingly, the detuned induction is the second most rigorous according to colleagues. That's not the same as undergraduates. They thought that was a lot less rigorous. Yeah, so that's exactly what we expected. Look where the picture is on rigour. That picture is of average rigour. That's not the message we give to undergraduates, is it, about using pictures, I think. It's kind of interesting. So pictures by themselves are not unrigorous. It definitely gives people, well, it's at the top of the insight scale, but there are error bars there. And the simplest one was 5, which was reversed lists, I think. Yeah, 5 was reversed lists. So the simplest one is reverse lists, not the picture. Anyway, we could chew over all of that forever, but I'm just going to move on with the talk, okay? Because there's a lot there to say. But it's kind of interesting, isn't it? There is stuff to discuss here. We did get this comment from one of our colleagues. Sorry, I consider both proofs as correct, and it doesn't make any sense to call one of them more rigorous. Okay? So for this colleague, rigour is a binary variable. It's either rigorous or it's not. Okay, that's a position to take. I don't agree with that. I think we've established that there is a scale, okay, and that scale is reliable. So I don't agree with this colleague, but they took that position and they were consistent on it. This is interesting. Whether this is a rigorous proof depends on the audience. For experienced mathematicians, yes. For first-year undergraduates, no. So that's another interesting, does rigour depend on the audience? Now, I've been acting as if rigour is a property of the proof, in which case it shouldn't depend on the audience. But this colleague thinks it does depend on the audience, right? That's sort of, you earned the right to use the picture. I think there's something in this. I think it's related to the expert reversal effect, which is a well-established psychological phenomenon. Expertise is described as the ability to perform fluently in a particular task or a particular class of tasks. And the effectiveness of an instructional technique might be reversed depending on whether you're the expert or not. So let's think about that proof by induction just for a minute. I want my first years to use the template. I expect them to use the template. Marks will be awarded whether or not they use the template. I'm being quite directive, and I'm doing that for a reason, because it's liberating to not have to worry about whether you've got the right template. Of course, it's a pain to write that out. If you know what you're doing, that does get in the way. It's all that, let P of n be the statement, blah, 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 blah. Experts don't need that, but beginners do. So this conscious honesty about this well-established expert reversal effect might be what this colleague is driving at here when they're talking about rigour. So I think that's kind of interesting. Okay, so this does beg the question when two proofs are the same and when they're different. And this led on to an interesting philosophical paper with a philosopher, Fenner Townswell. Of course, I don't think it's very interesting to talk about the induction proof, right? How much detail have I put in and taken out? That's not really the interesting thing here, to me. I'm very interested in steps, what constitutes a legitimate step, because I'm trying to mark students' work automatically on the internet. So this does come in for me a lot, and it's not related to the algebraic difficulty of a particular step. Because sometimes in real analysis you take a step which at a mathematical level is completely trivial, but actually that's a big hump over which you have to get. So if you try and measure the mathematical complexity of a step, like adding 0 would be cheap, wouldn't it, normally? It's not like expanding out the brackets or something, right? You know, or doing something factorizing. That would be a more expensive step. But so the importance of a step or the significance of a step is not really related, I don't think, to its mathematical difficulty. So deciding what is and isn't a legitimate step is quite subtle, but I don't think that's what we mean about deciding whether two proofs are the same or different. Now, Ben Davies is from Auckland. He did his PhD in the UK. He's now working at Southampton. His PhD was on writing proof summaries. And one of the participants in his thesis described a proof as a checkable record of reasoning, which I like as a phrase. What is a proof? And he talked about proof summaries. A summary is the minimum information from which another competent person could readily reconstruct this particular proof, right? So this idea of taking away all the unnecessary detail, what is the minimum information, and then reconstructing a proof from its summary. There's all sorts of proof-based activities that we don't, typically in the UK at least, ask our students to undertake that could be quite valuable associated with proof. But there's another sense in which proofs might be the same or different. So I'm going to focus on this proof. What's the essential idea in this proof, right? This is the proof where we take all the odd numbers, we take all the numbers, we subtract the even numbers, right? How could we draw a picture that represents the same algebraic argument? So Fenner and I were emailing back one summer, can we draw a picture which is the same as this algebraic argument, or what would be an algebraic argument that represents this picture? Yeah, is that even a meaningful question? Well, after a lot of toing and froing, this is the picture, this is the best picture that we can come up with that represents that proof. You take all the numbers, you rearrange the even numbers into two lots of the sum from 1 to n, and what do you get left with? The square. Okay, that's the idea, isn't it? So what does it really mean for two proofs to be the same or different? And when Fenner and I examined this whole collection of proofs, many of the proofs actually used only 3 basic essential ideas. Right? There's the reversed lists idea, and here is a picture of our reversed list, so 1, 3, 5, 7, and then we count backwards. That was the reversed algebraic list. Well, that is an arithmetic progression, uses that idea. So for that idea, there was a picture, a specific argument, and a general theorem, right? The second idea was the difference of adjacent squares is odd, okay? And then the third idea was that we rearrange things until we've got a basis of known results. So we can 1 plus 1 plus 1 plus 1, we know what that is. 1 plus 2 plus 3 plus 4, we know what that is. 1 squared plus 2 squared plus 3 squared plus 4 squared, we know what that is, right? If we can reduce the problem that we're interested in to a basis of known results, we can solve the problem. Now that's another idea. So all of our proofs, not all of our proofs, many of our proofs used one of these 3 ideas. So in fact, we didn't use this picture proof as one of our proofs in the experiment. This was one of the cases where we thought, oh, well, it's obvious what the picture proof is for that essential idea. Let's draw the picture. On the other hand, we had other algebraic proofs where we were trying to draw a picture of the algebraic proof, backwards and forwards. Here is the difference of adjacent squares is odd. That's the telescoping argument. That's the fundamental theorem of finite differences. That's the proof by induction. They always use that idea. And then the basis of known results, we tried to draw pictures to represent how would we get the basis of known results. Well, we're trying to, there's 1 plus 1 plus 1 plus 1. Here's 1 plus 2 plus 3 plus 4. We went through lots of iterations of this. This may not be the most convincing picture. Anyway, that was our goal. Rearranging and basis of known results. Okay. So all of that, I mean, there's quite a lot in this, trivial theorem, right? I mean, that's just made me think about the nature of the subject. Teaching the subject is often theorem, definition, theorem, proof. But actually, the general theorem is the collection of objects for which that essential idea works. Why are we interested in arithmetic progressions? Because we can sum them. They are the collection of things for which this idea works. Right? That's the idea, isn't it? So the definitions formalize the collection of objects. So teaching is often definition, theorem, proof. Research is often proof. I've had a good idea, theorem, and I've collected together all the things for which my proof works. Some research works like that. Okay. So, I think the comparative judgment methodology worked well. It was a reliable methodology, thanks to Ian for his code. I think these collections of proofs, I think collecting proofs was a valuable activity. It was a lot of fun. I commend it, right, as something to do. Of course, we want students to write proofs, and this collection of proofs, I've used this collection in my teaching, I'm now using other collections in my teaching. Of course the goal is to get students to write proofs, but write proofs in a particular style, or comparing proofs. Some proofs have different merits. Ben's proof summaries, proof comprehension, do you understand a proof? There are lots of activities associated with proofs, whereas in the past in my teaching I was mainly saying to students, just write this proof. But I'm being a lot more varied in activities associated with proof, and I think that's valuable. There are already many collections of proofs. Loomis's book has 270-something proofs of the Pythagorean theorem, right? A slightly crazy book. This book, Rationellement Q, 65 proofs that root 2 is irrational. Don't be put off by the fact it's in French. It's a great book. That was the book that inspired Ording, it turns out, to write his own. I wrote a collection of proofs for Heron's formula, which is the area of an arbitrary triangle based only on the 3 side lengths. So it's some nice result that's an algebraic result about a geometrical theorem. So it's right in the middle. And Fenner and I were joking that we should found the International Journal for Needlessly Repetitive Proofs. We probably won't, because that will spoil the fun for everyone else that wants to collect their own. Anyway, there we are. We investigated students' understanding and conceptions of rigour and insight. We conducted some comparative judgment experiments. We predicted and found that rigour is a reliable construct on this scale, and I think on the basis of that, we can be confident that we can meaningfully talk about rigour as a thing. But insight was, we thought that would be reliable, and we turned out that it wasn't. That is of itself an interesting result. I know negative results are not so attractive, but that's what we found. And I think comparing the relative merits of different proof has real teaching potential that I'm just beginning to explore. Okay, let's stop there. Thank you.
Thank you so much, Chris. We are in negative 2 minutes according to my watch. So maybe someone would just like to raise a thought, a comment, or a question as an encouragement to all of us to continue communicating with Chris when we go back to science. Yes?
I might have missed